Okay, so welcome to the first lecture for week 3. As I said in an email, I can't be at university today, so this replaces the Monday lecture for week 3. Okay, so where were we? Last week we were looking at linear independence, basis, and dimension. So in particular, we showed that every finitely generated vector space has a basis, and moreover, every basis of such a space has the same number of elements. That leads to the notion of dimension, which is really the single most important kind of numerical statistic for a vector space. In lectures this week, we'll start looking at linear transformations, and that'll lead us into matrix representations of linear transformations. And sort of the idea here is that so far we've been looking at vector spaces as kind of inert objects, just the vectors in the vector space themselves. And now we start looking at functions from one vector space to another that preserve the vector space operations, but in particular are moving the vectors around and doing things. So in this way, linear algebra becomes more dynamic. These linear transformations are often something that, well, in applications would be something that describes some system, some Markov chain, and the multiplying by a matrix gives the probabilities of the next step and the next step and so on and so forth. So these would be linear transformations. But in this course, we'll look relatively abstractly at linear transformations. So what are they? Well, we have to start with two F vector spaces, V and W. Then a linear transformation is a function from V to W, which, as I said earlier, preserves the vector space structure. So that means that lambda, theta of x plus y is theta of x plus theta of y for all x and y. So it preserves addition, and theta of lambda x equals lambda theta of x. And that one's for all x in V and lambda in the field. I guess it's worth noting that here we've got operations here in V, and over here, these are things that live in W, so these are the operations in W. And also note that V and W have to be over the same field. Okay, so linear transformations are only things that we define, only make sense when V and W are both F vector spaces for the same field F. Vector spaces are called isomorphic, written V squiggly line W, if there's a bijective linear transformation between them, and then that bijective linear transformation is called the vector space isomorphism. Okay, so the idea of an isomorphism is essentially if there's an isomorphism between two spaces, they're really the same thing up to what we've called the elements of the vector space. Okay. More generally, we're looking at linear transformations which are not bijective, just called a linear transformation. Okay, and we're going to talk about these for the next really sort of 4 weeks or something, really. It's the key part of linear algebra. So first note that the conditions 1 and 2 in the definition can be replaced by a single condition. That can be theta of lambda x plus mu y equals lambda theta of x plus mu theta of y. So that single condition is encapsulating that we preserve both operations, or put another way, we're preserving linear combinations. It's another way of saying that. Okay, linear transformations are also called just linear maps, sometimes for abbreviation, and they're also called vector space homomorphisms. Okay, so sometimes I'll call them that, and sometimes I'll call them linear transformations. As a remark or an exercise, really, that if theta is an isomorphism, then the inverse function, well, since theta is bijective, it has an inverse function, then the inverse function is also an isomorphism. So for that, you need to check the inverse function is a linear function, and, well, it stays bijective, of course. Okay, great. Basic properties of linear transformations. So we'll have some examples in a few minutes, but basic properties of linear transformations. If we have a linear transformation, then first of all, it maps the 0 to the 0. So to emphasize where these zeros live, I'll temporarily at least put subscripts there. So that's not part of the axioms of an homomorphism, vector space homomorphism. That's a property that we can prove. And also what it does to additive inverses, it maps the additive inverse of V to the additive inverse of theta V. Okay, so not really a surprise, these things, but we have to prove them. So let's prove one. We have, so I'm going to use here that 0f, there's multiple ways of proving these things, but since we've already shown that 0 times anything is 0, and similarly, oops, anything in W, I get 0 of W. We have that theta of the 0 vector of V is theta of 0 times 0 in the field times 0 in the vector space. A lot of zeros going around. This is 0 in the field times theta of 0 in the vector space. This is 0 in the field. Well, this is just 0, sorry. With the squiggle underneath it. This is 0 in W. So what are we doing here? This one here is by linear transformation. And the other two equalities are by the thing I wrote in a bracket up above. Okay, for 2, oops, not in red. So in 2, we have theta of minus V is theta of minus 1 times V. So that's something we proved at some stage in lecture 1 or 2 or something, lecture 2, when we introduced vector spaces. And that's minus 1 of theta of V. And, well, again, using that same factor we proved in week 1, that's minus theta of V. All right, so this is these two things are week 1. And this one is the linearity. Okay, good. Vector spaces map 0 to 0, and they map the additive inverse to the additive inverse. Okay, time for some examples though. Let's do a geometric example first. So let alpha be a real number, and let t subscript alpha be the map from the function from R2 to R2 given by rotating the vector xy by alpha radians clockwise. So here's a little picture. We've got our vector xy, and then I've swung it around by alpha to t subscript alpha of xy. And to derive the formula for t alpha, we'll write x and y in polar form. So r cos beta, r sine beta, where beta is the angle shown. And then let's compute away. So what is this, this function? Well, t alpha of xy in its polar, to rotate by alpha radians clockwise, we add alpha to the argument there in the polar form. And then we'll just expand out using some trigonometry identities. So double angle formulas. All right. And then remember that x is r cos beta and y is r sine beta. So we'll rewrite what we've got here. This is cos alpha times x minus sine alpha times y, I think. And then sine alpha x plus cos alpha y. And we unpack this as a matrix multiplication. This is cosine alpha minus sine alpha, cos alpha times xy. So this is just some matrix times xy, where our matrix here is that one, cos alpha minus sine alpha, cos alpha. So this is just matrix multiplication here. Actually going to show that every in a few minutes, we'll show that every linear transformation from Fn, F superscript n, so the n-dimensional vector space over the field F, to Fm is given by a form like this, just multiplying by a matrix, where that matrix will have to have n rows and m columns. Is that right? M rows and n columns. Sorry for the matrix multiplication to make sense. Okay, but we haven't actually checked that, we haven't proved that T alpha is a linear transformation. We have to show it satisfies the definition of a linear transformation. It's not entirely obvious from the definition, perhaps, by rotating by alpha. But anyway, once we've got this formula, it is clear because T alpha of, let's do it in the compact way, where we just prove the one formula that proves everything for a linear transformation. So lambda xy plus mu x prime y prime, that's now a matrix product here. So I can expand out in that middle row just doing matrix multiplication, and that's the corresponding thing with the t's. So basically what I'm piggybacking off there is that I know how to expand out matrix multiplications, though I know associativity of matrix multiplication, basically. Okay, so that's indeed a linear transformation. And we'll come back to that, as I said, this case of just multiplying by a matrix, that'll be what I'll call the key example that we'll get to in a little bit. All right, more examples, some more kind of exotic, let's say, examples of linear transformations. So now let's look at the vector space of all polynomials with coefficients in a field F. So not the real numbers or anything necessarily, just any old field. Then we can define something called the formal derivative of the polynomial by, well, it's by the formula you would expect. Not in red. Black. It's a1 plus 2a2x plus 3a3x squared, just by the normal formula for differentiation that you know and love. And I've got these things 1, 2, 3, 4, up to n appearing there. What do they really mean? Because I'm working in a field that's maybe not the real numbers or something, so they're not really the n from the real numbers. What n means there is 1 plus 1 plus 1 plus 1 n times in the field F. We discussed that, I think, back in week 1. So for example, if f of x was 1 plus 3x squared plus x to the 5, in Z5 of x, and I think I'm going to try to use the F notation here instead of Z for use that, but it's the same as Z5, but I think I'll use F more. Then the derivative is, well, I just get 6, which is 1 though, so 6x. And then now this 5 comes down to get 5x to the power of 4, but 5 is 0 in Z5, so that's all I get. It's just that. Okay, so that's the formal derivative. You'll actually see next year in the Galois theory course, this formal derivative actually has some significance, in particular in detecting when you have multiple sort of double roots of a polynomial over a field. It's quite a useful thing, in fact. But what we're looking at here is that this is a linear transformation. So it's a linear transformation from all polynomials to all polynomials. Of course, I could also consider it as a linear transformation from polynomials of degree n down to polynomials of degree n minus 1, if I like. That would also be, but anyway, here we go. It's a linear transformation. We'll just prove it directly. So let f and g, f of x and g of x be polynomials. And just to fix notation, let's take n to be the biggest of the 2 degrees. That just will help me write out, when I'm writing out my formulas for f and g, that'll help in writing stuff down. So then f of x is the sum I equals 0 to n ai xi, and g of x is the sum bi xi. And the reason I've taken this n to be the maximum degree, so I've just, whichever one, if one of them had a smaller degree than n, I've just filled up its coefficients with 0 so that I can write them both as sums up to n. Anyway, that's just so that, just to save me a bit of a headache. So then for lambda and mu in the field, we have d dx, this formal derivative of lambda f of x. Well, I didn't use d dx notation earlier. Maybe I'll write it with the prime. We have lambda f of x. I've called it d. Sorry, that's better. Use the capital D. Capital D of lambda f of x plus mu g of x equals, so by its formula, it's the sum from I equals 0 to, well, yeah, 0 to n minus 1, I guess. Oh, no, that's right. I, and then I do lambda ai plus mu bi. Yeah, I think that's right. X, and I bring the power down by 1. Okay, that's just the definition of the formal derivative. But then, of course, this breaks up into a sum of two things. Oops, oh yeah, that's right. Lambda I ai x to the I minus 1 plus mu. Anyway, not rocket science, of course. And this is what we were after. This is lambda d of f of x plus mu d of g of x. Okay, good. So that's a linear transformation. And just for notation, we write these things, and maybe we'll also write, so the double derivative means what it means, of course. And also, excuse me, phone's beeping. And also, maybe I will occasionally use this notation d dx to be just synonymous for that. Okay, good. So that's another example. But now we'll get to the key example. So let A be an M by N matrix with coefficients in our field, entries in our field, and let theta be given by theta of V equals A times V, sorry. Then theta is a linear transformation, and this is really what we did for the rotation example, because this is, this is just A times V plus W, and that's AV plus AW. And there I'm just using matrix multiplication, distributivity of matrix multiplication. Sorry, I said associative earlier. I think I meant distributive. And there we are. So similarly, for the lambda V equals lambda of theta of V. Okay. But conversely, the point is every linear transformation from Fn to Fm is of this form, just by a matrix multiplication. So what we're saying in this bottom line here is actually that the class of linear transformations from the vector space Fn to Fm is really just the same as M by N matrices. Now, just to make a comment, if our vector spaces weren't Fn and Fm, then you can't write it necessarily like this, but as we'll discuss a bit later on, actually, Fn, we could always, if we have an n-dimensional vector space, it's always isomorphic to F superscript n. So we can always sort of rewrite theta in this matrix way after fixing isomorphisms of our n-dimensional space with Fn and our m-dimensional space with Fm. But actually, I'm getting ahead of myself. That's really what we'll talk about on Tuesday. with matrix representations. All right. Anyway, but I want to prove this, of course. So I'm saying conversely, every linear transformation is of this form. And to see this, first note, it's convenient to note the following fact, which is useful to have in your mind anyway. And that's that if we have a linear transformation from V to W and a basis of V, then the linear transformation is uniquely determined by its values on the basis. I mean, before even writing out the proof, this should be pretty clear. Every element of V can be written as a linear combination of elements of the basis. Linear transformation, by definition, sort of preserves linear combinations, like it'll break up into a linear combination of the images of the basis elements, and hence it'll be determined by the basis elements. But we just prove it, I guess. So for the proof, it's exactly what I said. So if V is in V, then V can be written as I in I, with lambdas. Then by linearity of theta, we have theta of V equals. So really what I'm doing here is it's sort of a big induction that I'm never going to write out formally. Of course, the definition of a linear transformation just told me I could break up a sum of two things, but of course I can break up a sum of lots of things, like I'm writing now, just by induction. Okay, and so theta is indeed determined by the vectors theta of Vi. So just in other words, if you've told me what theta does to all of the basis vectors, I can reconstruct what it does to every element of V using this formula on the second last line here, this one here. Okay, but anyway, back to our proof of the sort of claim here. So now to prove the claim. Reminder what that claim was. That claim was that if we have a linear transformation from Fn to Fm, then it's really just given by matrix multiplication. So to do that, let's let A, maybe with the subscript theta or something, be, well, let's write M or something, M for matrix, M of theta, be the matrix whose first column is the image of the first basis vector of Fn, and whose second column is the image of the second basis vector, and so on and so forth. Fn is Fm, so these are, sorry, Fn, so there's n of these things. Where E1 up to En is the standard basis of Fn. So these guys here are columns, these are column vectors. In Fm. So that means this matrix has m rows and n columns. So m rows, n columns. All right. Where they're the base vectors of Fm. Okay, so in particular, by the way matrix multiplication works, if I look at m theta applied to just matrix multiplication onto an EJ, then this equals theta of EJ. And so what that means is this linear transformation given by multiplying by m theta does exactly the same thing to the standard basis as theta does. So it's the same as theta by the proposition above. Okay. So anyway, just to emphasize that again, so it's when we're linear transformation is from our favorite vector space, let's say Fn to Fm, then it's just multiplying by a matrix. So linear transformations are sort of nothing more than matrices in that sense. Okay, so continuing on with that theme actually. So let's say we have theta being a map from R3 to R4, and given that proposition that we proved, I can define this linear transformation by just telling you what it does on the basis vectors. So it's the unique linear transformation that maps these three standard basis vectors to these three other vectors that I've said. So then by what we just discussed, but I changed this notation to m theta, so I'll change it here too. Where m theta, it's just this matrix consisting of these three columns, that's all. Okay. Good. So let's discuss now kernel and image. These are important definitions. So we have a linear transformation from V to W. And now the kernel and image are special. First one is a subspace of V, and the second one is a subspace of W, and they're defined in the following way. So the kernel is the all the things which are killed by theta. So this is kernel of theta. It's all of the V's in V, such that theta of V equals 0. And the image is, well, all of the outputs, so to speak. So the image of theta is all of the theta of V's, such that V is in V. Okay, so you probably remember kernels and images a little bit. So if theta was just given by a matrix, so if it was going from Fn to Fm, then the kernel of theta is just all of the vectors such that AV equals 0. So it's the 0 eigenspace, for example. Okay. Right. But we have some important properties of kernel and image. I already said the first two, actually. I said that the kernel was a subspace of V, but we should prove that. The image is a subspace of W. Again, we should prove that. Theta is injective if and only if the kernel is trivial. That's a very important characterization of injectivity. And theta is surjective. Well, this is by definition, this last one. It's surjective if and only if the image of theta equals W. So part 4 is really just the definition of surjective, in fact, but part 3 we'll have to prove. Okay, so let's get on with it. So the first one, to show that kernel is a subspace, let me leave that one as an exercise, and you can do that using subspace criteria. But let's prove properly that the image is a subspace of W. So first of all, we have the zeros in there, so we proved that earlier. 0 of W is theta of 0 of V, and so the 0 vector is certainly in our image. So it's not empty. Now, if W1 and W2 are both in the image, then I want to show that W1 plus W2 is in the image, and also lambda times W1 is in the image. Well, to be in the image, it means there is V1 and V2, V1 and V2 in V, such that W1 equals theta of V1 and W of 2 equals theta of V2. So that's just the definition of being in the image. But then W1 plus W2 is, maybe I'll just do this one in one go. I'll do the one, it's a bit, could do a bit quicker. W1 plus mu W2 equals, so this is theta lambda of theta of V1 plus mu of theta of V2. But now this is exactly set up so that I can use the property of being a linear transformation. And so this is in the image of theta. Why is it in the image of theta? Because I've expressed it as theta of something, and that's what it means to be in the image. Okay, so it is a subspace of W by subspace criteria. The next thing we wanted to prove was that theta is, scroll up a bit, theta is injective if and only if the kernel is trivial. So let's prove that carefully. So if theta is injective, then in particular, theta of V equals 0, which is also theta of 0, forces. So injectivity means when theta of x equals theta of y, then x has to equal y. So that says that V has to equal 0. And so that's the same as saying the kernel of theta is just 0. But conversely, if we know that the kernel of theta is, if we assume the kernel of theta is trivial, then prove injectivity by saying, well, theta of x equals theta of y, but that's the same as saying theta, well, that implies theta of x minus y is 0, and that implies that x minus y equals 0. Well, maybe I'll unpack it really slowly, that x minus y is in the kernel. So that's saying x minus y equals 0 by assumption, because the kernel is 0. So x equals y. Hence, injective. And 4 is, as I say, is just by definition. 4 was saying you were surjective if and only if range equals codomain or image equals codomain. That's actually the definition. Okay, I would stop for questions, but of course it's a recording, having a bit of a flashback of COVID actually. All right, what's next? All right, just a remark now, you probably remember column space from last year, and we'll discuss it a little bit at some time, or it comes up every now and then. So the column space of a matrix is by definition just the subspace spanned by its columns, and similarly the row space is the subspace spanned by its rows. So column space, if it's an M by N matrix, then it's got M rows, so each column has length M, so that's a subspace of Fm. And the point of this remark here is that if A is in an M by N matrix over F, and if theta subscript A is the one given by the linear transformation given by just AV, then the image is actually the same as the column space. So in fact, yeah, so just maybe a philosophy for moving forwards. We'll be doing things like Jordan normal form for matrices, but it's actually much more convenient to think of these things as being properties of linear transformations. And we've already discussed there's this connection between linear transformations and matrices, but the best thing about working with a linear transformation instead of a matrix is that linear transformations have no particular basis attached to them. Whereas matrices, you have to have fixed a basis and written your everything as F in Fn as column vectors and all that kind of stuff. So linear transformations are much more versatile, even though they're equivalent in a certain sense to matrices, they're much more versatile. Anyway, so I'd prefer to talk about the image rather than the column space is what I'm talking about, is what I'm trying to say. But we should see this, so we'll write A to B, just have some columns, we'll just name its columns. So V1 up to Vn, where these VIs are in Fm. So I'm trying to show that the image is the same as the column space of A. So V is in the image of A, image of theta A, sorry. if and only if V is of the form A times W for some W in Fn, and that's if and only if V equals, well, let's just write out what A is again. It's V1, Vn, right? N. And W is lambda 1. Let's call it lambda 1 up to lambda n, with lambda i's in F now. And that's, by the way, matrix multiplication works. That's saying V equals lambda 1 V1 plus dot 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 plus lambda n Vn. And that's saying if and only if V is in the column space of A. Okay, so remember that that fact that the image, if a linear transformation is given by matrix multiplication, then the image of that linear transformation is exactly the column space of that matrix. All right, great. Let's do another example. So now let's change fields. Let's go to, well, not change fields, but let's specify a field. So we'll go to the field with 3 elements, which is Z3, and consider theta from the 4-dimensional space over that field to a 3-dimensional space over that field, given by this here, and we want to compute the image and the kernel. Well, first, actually, to compute the image, it's easiest just to read it off as the column space. That's a span of 1, 1, 1, 2, 0, 1, 1, 2, 0, and 0, 1, 2. Okay, that's the image. Often we don't want to just say, okay, that's the image. We want to find a basis for the image, describe it a bit better. And we discussed that in week 2. And what we did was we put these 4 vectors into a matrix. Well, that gives us our matrix that we started with, actually. And then just row reduce that matrix to row echelon form. Well, don't have to go all the way to reduce row, but just row echelon form. And then the columns of that row echelon form that have the pivots, which are the leading ones, we take the corresponding columns of the original matrix A, and that forms a basis of the column space, or the image. So let's do that. So we have A, it's this matrix. I'll just cut and paste it, I think, is intelligent. And we row reduce away, do lots and lots of row operations. And I did this earlier, and I get this. There's 2 pivots there, this guy and this guy. These are the pivots. And so the corresponding columns of A, which are the first and second, 1, 1, 1, and 2, 0, 1, give a basis of the image of theta. To find the kernel is also row reduction, in fact, so it's a bit of repetition. Maybe we could have done it sort of well, in fact, we don't have to do it again. I've done the row reduction, so I can just write it out again. So to find the kernel, also do row reduction. Because what are we trying to do? We're trying to solve that V is in the kernel. Well, what does it mean to be in the kernel? V is in the kernel if and only if AV equals 0. So we're trying to solve a matrix equation. So we solve that. We just write A augmented matrix with 0, row reduce. Well, we worked out what A row reduces to earlier. And yeah, having a column of zeros on the right-hand side, that'll stay as a column of zeros through that process, so we don't have to go through and check anything there. And so we get two free variables, x, y, the variables, let's call the variables, I don't know, got to give them names, x, y, z, and w. So z and w are free. Because they're the columns which don't have a leading one. So here S and T are in our field, which was F3, I think, right? Good. And then Y can be computed in terms of those. That's minus Z minus W. So that's 2S plus 2T. And X equals minus 2Y minus Z, which is, I think when I worked it out earlier, it was S plus 2T. So let's just say that. Sorry, T plus 2S. And so the kernel of theta is all of the vectors T plus 2S, 2T plus 2S, T and S, with S and T in F3. But I guess I should write that in a nicer way. That's a span of two vectors, 1, 2, 1, 0 times T plus 2, 2, 0, 1 times S, with S and T in F3. So that's indeed the span of 1, 2, 1, 0 and 2, 2, 0, 1. Good. And it's also clear that the vectors you'll get this way by solving this way, they're definitely linearly independent. And you can see that by where there's a 0 in, so the first vector has a 0 in the fourth row and the third one has a 0 in the third row. So you certainly can't use a multiple of the first vector to get the second or anything like that. Okay. So that'll always be the case. They'll come out to be linearly independent when you do row reduction. All right, good. So going a lot quicker with that without questions. So I guess we just keep going. Of course, you can pause it whenever you like. So as an exercise, consider the formal derivative, which I'm calling D again. So D from polynomials to polynomials. Compute the kernel and the image, but of course it'll be a little bit different depending on what the field is. So compute the kernel and image when the underlying field is considered to be the rational numbers, and then do it when it's the field with 5 elements. All right, enjoy that exercise. The next section, section 3.3, where is the classification of finitely generated vector spaces. We could have done this a little bit earlier, I guess, but we have to talk about the notion of isomorphism of vector spaces first. But the point of this section is to say that up to isomorphism, there's a unique F vector space of dimension n for each n. Okay, but we'll get there. So first there's this proposition, which is just telling us how linear transformations and bases interact, or more generally, how the concepts of linear independence and spanning set interacts. So it goes as follows. So let's say theta is our linear transformation from V to W, and let B be a basis of V. Then theta is injective if and only if the image of this basis is linearly independent in W. Theta is surjective if and only if the image of this basis spans W. And theta is an isomorphism if and only if, well, both of those things happen, and so therefore a basis of W. Okay, so this is quite, in particular, the third part is the one that you use quite often, that theta is an isomorphism if and only if it maps a basis in V to a basis in W. Okay, so maybe I'll write that again. Theta isomorphism if and only if it maps basis in V to basis in W. That's the sort of punchline, actually. All right, but we'll prove this. So first one, suppose theta is injective. And let's say we've got a linear combination that equals 0. I'm trying to show linear independence, so I'll take my linear combination equaling 0 and show that all the coefficients have to be 0. Well, then theta of this sum, oh, sorry, that sum with the VI, that's the same as the thing up above, so that's 0. So this sum is in the kernel of theta. But since we're assuming injective, well, maybe since theta is injective, kernel of theta is 0 from what we proved earlier. So hence sum lambda I vi is 0, but the vi's were a basis, so they're linearly independent. That's basis, hence in particular linearly independent. Okay. So I've only done one way there, I guess, though, right? So if theta is injective, so okay, for the converse, let's leave that as an exercise. That's a nice one. 2 we'll leave also as an exercise. And then for 3, well, it's nothing to do. It follows from 1 and 2. Okay, good. So that proposition gives the following quite sort of striking consequence, which is also very useful. So we'll call it the classification theorem for vector spaces. So if we've got 2 finitely generated F vector spaces, so they're over the same field F, then they're isomorphic if and only if they have the same dimension. In other words, that's saying that once we fix the field F, then for each n, dimension 0, 1, 2, 3, and so on, there's only one vector space up to isomorphism of that dimension. When you read something like that, you might think, well, why do we care about the other vector spaces like polynomials of degree n? That's an n plus 1 dimensional vector space. Why don't we just consider that as f n plus 1? But the reason is that often the vector space given to you in some other more natural like matrices as well, and m by n matrices is a vector space of dimension m times n. So you could consider them as huge, big, long column vectors, but matrices have this additional structure of multiplication and so on and so forth. And trying to understand that when you're writing them all as big columns wouldn't really make sense. And moreover, linear operators between 2 vector spaces are often much more natural if the vector space is given in its kind of natural incarnation. Like, for example, polynomials and the differentiation operator, that would probably look a bit stranger if you define that linear operator just on Fn instead. But you could, you could define it there. Anyway, so I'm just saying we still care about all the different ways of the vector spaces arise, but we're saying that they're all isomorphic if they have the same dimension. So the way this goes, we'll prove, well, both directions. So suppose V is isomorphic to W. It's an isomorphism, not an equality there. And let theta be an isomorphism. Then if VI, I and I as a basis, then by the proposition, the image is also a basis in W. And so they have the same dimension. Okay, again, just to say that we're mapping a basis to a basis. Okay, injectively as well, because there is an isomorphism. It's not like squashing these things down or anything. Okay. Good. So conversely, suppose the dimensions are the same. Let's call it n. Now here we'll just construct an isomorphism from V to W. So there's lots of ways of doing that. You have to just pick bases of the two spaces and then map one to the other, basically, and that uniquely determines a linear transformation, and that'll be an isomorphism. And define function theta from V to W by, so a generic element of, sorry, it's sum I equals 1 to n. A generic element of V looks like that, and by definition I'll define theta of such an element to be this one here. Now all of this is well defined because every element of V has a unique way of expressing it like this. You know, if the expression wasn't unique, if there were multiple ways of writing a vector in this as this linear combination, then this wouldn't be a well-defined map, but it is. So then this is a linear transformation. It's almost immediate from the definition, so it's an easy exercise to check. And it is an isomorphism because CAUSE, because it maps the V's to the W's. So a basis to a sorry, I did something stupid up here. I meant to write W here, of course. Sorry. Yeah. WI. It's an isomorphism because it maps a basis to a basis. So V is isomorphic to W. Good. Okay, so that's the way that one goes. Yeah, let's go through this comment because we're going to follow on with this comment more tomorrow on Tuesday and also the week after, week 4. So it means that so it means that if V is an F vector space of dimension n, then V is isomorphic to our kind of favorite vector space Fn. The consequences that has is that Fn is very concrete. I mean, column vectors, and we can operate with matrices and stuff like that. And in particular, this implies that linear transformations from a finitely generated space V to a finitely generated vector space W are essentially the same as just matrices in m by n matrices. But to make that realization of seeing the linear transformation as a matrix, we have to make choices of the basis in V and a choice of the basis in W. Now those two choices let us identify V with Fn and W with Fm. And once we do that, we can write theta in terms of a matrix, and it'll be a matrix theta will act by matrix multiplication. we're going to do that next week. Okay, good. I think we'll do one more section and then finish. So I haven't used this notation yet. So HOM FVW, well, we've been talking about linear transformations for the last hour, but HOM FVW is just the space of all, sorry, the set of all linear transformations from V to W. The reason it's called HOM there for HOM is for abbreviation of homomorphism. Okay. And remember, homomorphism was another name for a linear transformation. Okay, so HOM VW. If the F is really clear, sometimes the F is omitted from that notation, but I think I'll probably just I quite like writing it there anyway, so I'll probably do that. All right, the first observation here. So, okay, so just to reinforce what we're doing here, like we were looking at individual linear transformations earlier, and now we're just going to put them all into a big set and look at all linear transformations together. The first theorem here is that this is in fact a vector space, an F vector space, and the operations are given here. So θ1 plus θ2 of V is θ1 of V plus θ2 of V, and lambda θ1 is the function whose value at V is lambda times theta of V. And I won't go through the proof of that. It's just, we can't use subspace criteria because we don't have this sitting inside some bigger vector space. So we in fact just need to directly check all of the vector space axioms. Directly check vector space axioms. So now we actually have a whole vector space full of all the linear transformations from V to W. And the very last thing I want to say before we'll finish is about composition. So if we have two linear transformations, let's say θ1 going from V1 to V2, and θ2 going from V2 to V3. Well, at this stage, I'm just saying they're functions, in fact, with these V's being sets. Then I define the composition in the way that you normally define it. θ2 composed with θ1 is the function θ2 of θ1 of V. Okay. And the proposition here is now we move back to vector spaces. So let V1, V2, V3 all be F vector spaces. And let's say we've got a linear transformation from V1 to V2 and a linear transformation from V2 to V3. Then the composition is again a linear transformation. And a bit more information here. If θ1 and θ2 are injective, then the composition is. And if they're both surjective, then the composition is as well. So in particular, if they're both isomorphisms, if they're both isomorphisms, then the composition's an isomorphism as well. And this one I'll leave as an exercise, just checking directly the definition. So, but we'll come back to it again on Tuesday, I think. But basically what we're saying here, we've got this vector space HOM VW consisting of all of the linear transformations. It's got its vector space operations, which is an addition and scalar multiplication. But now if we take the case that V and W are the same, so it's HOM V to V, then we'd also have composition of these linear transformations. So an extra operation. So that ultimately will make HOM VW into a more complicated object called an algebra. And we won't study it really concretely like that, but we'll discuss it a little bit more tomorrow. Anyway, good. So I hope it wasn't too much of a flashback of COVID. We'll be back tomorrow on Tuesday to talk about matrix representations of linear transformations. Okay, bye.